The McFarland Insurance Company Claims Department reports that the mean cost to process a claim is $60. An industry comparison shows this amount to be larger than most other insurance companies, so the company instituted cost-cutting measures. To evaluate the cost-cutting measures, the supervisor of the claims department selected a random sample of 26 claims processed last month and recorded the cost to process each claim. The sample is reported to the left. That's in column A. Those are the individual costs of the 26 claims. Use a 0.01 level of significance to determine whether it is reasonable to conclude that the mean cost to process a claim is now less than $60. Okay, the word claim is used a number of times in this problem, but the claim that we're referring to in the context of the hypothesis test, that's at the end of the problem. Use a 0.01 level of significance to determine whether it is reasonable to conclude the mean cost to process a claim is now less than $60. So that's the claim that we're testing. The mean cost to process a claim is now less than $60. So we start with that. So in this case, the claim that we are testing with this hypothesis test is that the mean cost to process a claim is less than $60. So once we have our claim given symbolically, which we do right now above, we can now set up our null and alternate hypotheses. And as always, the null hypothesis is a statement of equality, so we would say the mean is equal to $60, and the alternate hypothesis in this case is the same as the claim, that the mean is less than $60. Now the alternate hypothesis, that tells us what type of test it is, and it's the alternate hypothesis uses less than. So we have a left-tailed test. So our critical region is in the left tail, and that area of that critical region is alpha, the significance, which is given in the problem as 0.01. So that's the area of the left tail. Now, this is a hypothesis test about the mean, and we're not given sigma. We're not given the population standard deviation, so we're using the t distribution. And we have one critical value. It's going to be a negative number because it's to the left of 0. All right, so now let's go back to the problem, and let's pull out the information that's given. A random sample of 26 claims. Okay, so that's our value of n. In this case, n is 26. Okay, we're testing the claim that the mean is less than 60, and our null hypothesis is saying that the mean of all claims is $60. So the value of mu we're going to use, the assumed value of mu is 60. And the level of significance given in the problem is 0.01. Now, we're not given the sample statistics, but we're given the sample data. So we need the sample mean, x bar, and that's the average of the sample, so equal average of column A. You could just click on the A. And the standard deviation. So equal STDEV.S for sample standard deviation. And we want the standard deviation of those numbers in column A. All right, so now we have the mean and the standard deviation. Our significance is what we use to determine the critical value. And so our critical value over here is that t value that separates the lower area of 0.01 from the other area 0.99. Okay, so to determine that critical value, we have our t distribution functions, and in this case, we're going to use equal t dot inv. That's the inverse of the t function. Probability is area to the left. So in this case, it's alpha. It's the 0.01. And we need the degrees of freedom. So in this case, the degrees of freedom is equal to n minus 1. So equal, I don't need equal sign, equal n minus 1. So in this case, 25 degrees of freedom. Okay, so now we have our critical value. That's the negative 2.485. Now we move on to the test statistic, or the p-value. In this case, we're going to do both. So that's what we use to determine whether or not to reject the null hypothesis. Now, the test statistic in this case is a t-value, so t equals, and it's the difference between the sample statistic and the assumed population parameter, so x bar minus mu, and we divide that by the standard error between x bar and mu, which is s divided by the square root of n. Okay, so let's put that in here for our test statistic, and we could use parentheses for the numerator and also the denominator, so we'll make sure Excel follows the order of operations that we want. Okay, so test statistic equal x bar, which is here, minus mu, which is here in C15, close parentheses, and we'll divide this by, and again I'll put parentheses around the denominator, standard deviation of the sample divided by the square root of n, the square root of the sample size. So divided by SQRT, parentheses, of n. So n is here at C13. Close parentheses, close the other parentheses, and that should do it for the test statistic. Okay, so our test statistic is negative 1.817. So that's, let's give it a little bit of room. Test statistic, TS, so it's negative 1.817. So our sample data, we've converted to this one single value to sort of represent that sample, and that test statistic is not in the critical region. So that tells us we fail to reject the null hypothesis. Fail to reject the null hypothesis. That's the traditional method of a hypothesis test, and we could also talk about the p-value method. And the p-value, well, we need the area outside of the test statistic. Now, just by this diagram, we know it's larger than alpha, but let's just determine what that p-value is. So that p-value should be the area to the left of negative 1.817. So we'll use the other t distribution function equal t dot dist for t distribution. Our x value is the test statistic, or what Excel is calling an x value. If we know it's a t value. The degrees of freedom, we know that's n minus 1. So there's n. We could subtract 1 from that, n minus 1. And cumulative, for that final input, always use a 1. Okay, so our p-value, it's going to give us something larger than, well, it should, if we've done everything right, it should give us something larger than 0.01 and 0.041. So yes, the p-value, in this case, the p-value of 0.041 is greater than the significance, alpha, which is 0.01. And so that also tells us fail to reject the null hypothesis. So this is the p-value method. Over here is the traditional method. Always these two methods give you the same result. If one method says fail to reject, the other one is going to say fail to reject, and vice versa. Okay, so now we know we are not rejecting the null hypothesis. That's not the final answer. The final answer. This is basically the step before the final answer. The final result or the final answer of a hypothesis test is the conclusion. We have to state the conclusion. And for that, I could go over to the other sheet that I have in this file. So under charts, let's get rid of that from the previous problem that we just did. Now, two questions. The first question is, does the original claim contain equality? Does it contain an equal sign? No. The original claim was that the mean is less than 60. So the original claim contains a less than sign, not an equal sign. So that puts us here. Second question, do you reject the null hypothesis? No, we did not. So that puts us here. So this one's out, this one's out, this one's out, and here is our final answer. There is not sufficient sample evidence to support the original claim. And so when we state that, we want to be specific. Not sufficient evidence to support the claim that the mean of all of these insurance claims is less than 60. So basically, this is this hypothesis test was inconclusive, which means we need more sample data. Okay, so that does it for this problem. This was a left-tailed test, but just like with the proportion, which we went through in a number of videos, the hypothesis test or testing a claim about a population mean could be a left-tailed test, a right-tailed test, or a two-tailed test. So you determine which type of test it is always by the symbol used in the alternate hypothesis, whether it's a less than, a greater than, or a not equal to sign. Those are the only three options. Okay, that does it for this problem. I hope this was helpful.